The Higgs boson is an elementary particle in the standard model of particle physics. It is the quantum excitation of the Higgs field, a fundamental field of crucial importance to particle physics theory. First suspected to exist in the 1960s, that unlike other known fields such as the electromagnetic field, takes a non-zero constant value almost everywhere. The question of the Higgs field's existence has been the last unverified part of the standard model of particle physics and, according to some, the central problem in particle physics. The presence of this field, now believed to be confirmed, explains why some fundamental particles have mass when, based on the symmetries controlling their interactions, they should be massless. The existence of the Higgs field would also resolve several other long-standing puzzles, such as the reason for the weak force's extremely short range. Although it is hypothesized that the Higgs field permeates the entire universe, evidence for its existence has been very difficult to obtain. In principle, the Higgs field can be detected through its excitations, manifest as Higgs particles, but these are extremely difficult to produce and detect. The importance of this fundamental question led to a 40-year search and the construction of one of the world's most expensive and complex experimental facilities to date, CERN's Large Hadron Collider, in an attempt to create Higgs bosons and other particles for observation and study. On the 4th of July 2012, the discovery of a new particle with a mass between 125 and 7002127000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 Boson. Since then, the particle has been shown to behave, interact, and decay in many of the ways predicted by the standard model. It was also tentatively confirmed to have even parity and zero spin, two fundamental attributes of a Higgs boson. This appears to be the first elementary scalar particle discovered in nature. More studies are needed to verify that the discovered particle has properties matching those predicted for the Higgs boson by the standard model, or whether, as predicted by some theories, multiple Higgs bosons exist. The Higgs boson is named after Peter Higgs, one of 6 physicists who, in 1964, proposed the mechanism that suggested the existence of such a particle. On December 10, 2013, 2 of them, Peter Higgs and François Inglet, were awarded the Nobel Prize in Physics for their work in prediction. Although Higgs's name has come to be associated with this theory, several researchers between about 1960 and 1972 independently developed different parts of it. In mainstream media, the Higgs boson has often been called the God particle. From a 1993 book on the topic, the nickname is strongly disliked by many physicists, including Higgs, who regard it as sensationalistic. In the standard model, the Higgs particle is a boson with no spin, electric charge, or color charge. It is also very unstable, decaying into other particles almost immediately. It is a quantum excitation of one of the 4 components of the Higgs field. The latter constitutes a scalar field, with 2 neutral and 2 electrically charged components that form a complex doublet of the weak isospin SU symmetry. The Higgs field is tachyonic, and has a Mexican hat-shaped potential with non-zero strength everywhere, which in its vacuum state breaks the weak isospin symmetry of the electro-weak interaction. When this happens, 3 components of the Higgs field are absorbed by the SU and U gauge bosons to become the longitudinal components of the now massive W and Z bosons of the weak force. The remaining electrically neutral component separately couples to other particles known as fermions, causing these to acquire mass as well. Some versions of the theory predict more than one kind of Higgs fields and bosons. Alternative, Higgsless models may have been considered if the Higgs boson was not discovered. On 15 December 2015, 2 teams of physicists working independently at CERN, reported preliminary hints of a possible new subatomic particle. If real, the particle could be either a heavier version of a Higgs boson or a graviton. A non-technical summary. Higgs terminology overview. Physicists explain the properties and forces between elementary particles in terms of the Standard Model, a widely accepted and remarkably accurate framework based on gauge invariance and symmetries, believed to explain almost everything in the known universe, other than gravity. But by around 1960 all attempts to create a gauge invariant theory for two of the four fundamental forces had consistently failed at one crucial point. Although gauge invariance seemed extremely important, it seemed to make any theory of electromagnetism and the weak force go haywire. By demanding that either many particles with mass were massless or that non-existent forces in massless particles had to exist, scientists had no idea how to get past this point. In 1962, physicist Philip Anderson wrote a paper that built upon work by Yoichiro Nambu concerning broken symmetries in superconductivity and particle physics. He suggested that broken symmetries might also be the missing piece needed to solve the problems of gauge invariance. In 1964, a theory was created almost simultaneously by three different groups of researchers that showed Anderson's suggestion was possible. The gauge theory and mass problems could indeed be resolved if an unusual kind of field, now generally called the Higgs field, existed throughout the universe. If the Higgs field did exist, it would apparently cause existing particles to acquire mass instead of new massless particles being formed, although these ideas did not gain much initial support or attention. By 1972 they had been developed into a comprehensive theory and proved capable of giving sensible results that accurately described particles known at the time, and which accurately predicted of several other particles discovered during the following years. During the 1970s these theories rapidly became the Standard Model. There was not yet any direct evidence that the Higgs field actually existed, but even without proof of the field, the accuracy of its predictions led scientists to believe the theory might be true. By the 1980s, the question whether or not the Higgs field existed had come to be regarded as one of the most important unanswered questions in particle physics. If the Higgs field could be shown to exist, it would be a monumental discovery for science and human knowledge, and would open doorways to new knowledge in many disciplines. If not, then other more complicated theories would need to be considered. The simplest means to test the existence of the Higgs field would be a search for a new elementary particle that the field would have to give off. A particle known as the Higgs boson, or the Higgs particle. This particle would be extremely difficult to find. After significant technological advancements, by the 1990s two large experimental installations were being designed and constructed that allowed to search for the Higgs boson. While several symmetries in nature are spontaneously broken through a form of the Higgs mechanism, in the context of the Standard Model the term Higgs mechanism almost always means symmetry breaking of the electroweak field. It is considered confirmed, but revealing the exact cause has been difficult. Various analogies have also been invented to describe the Higgs field and boson, including analogies with well-known symmetry-breaking effects such as the rainbow and prism, electric fields, ripples, and resistance of macro objects moving through media, like people moving through crowds or some objects moving through syrup or molasses. However, analogies based on simple resistance to motion are inaccurate as the Higgs field does not work by resisting motion. Significance. Scientific impact. Evidence of the Higgs field and its properties has been extremely significant scientifically, for many reasons. The Higgs boson's importance is largely that it is able to be examined using existing knowledge and experimental technology, as a way to confirm and study the entire Higgs field theory. Conversely, proof that the Higgs field and boson do not exist would also have been significant. In discussion form, the relevance includes practical and technological impact of discovery. As yet, there are no known immediate technological benefits of finding the Higgs particle. However, a common pattern for fundamental discoveries is for practical applications to follow later, once the discovery has been explored further, at which point they become the basis for new technologies of importance to society. The challenges in particle physics have furthered major technological progress of widespread importance. For example, the World Wide Web began as a project to improve CERN's communication system. CERN's requirement to process massive amounts of data produced by the Large Hadron Collider also led to contributions to the fields of distributed and cloud computing. History. Particle physicists study matter made from fundamental particles whose interactions are mediated by exchange particles, gauge bosons, acting as force carriers. At the beginning of the 1960s, a number of these particles had been discovered or proposed, along with theories suggesting how they relate to each other, some of which had already been reformulated as field theories in which the objects of study are not particles and forces, but quantum fields and their symmetries. However, attempts to unify known fundamental forces such as the electromagnetic force and the weak nuclear force were known to be incomplete. One known omission was that gauge-invariant approaches, including non-abelian models such as Yang-Mills theory, which held great promise for unified theories, also seemed to predict known massive particles as massless. Goldstone's theorem, relating to continuous symmetries within some theories, also appeared to rule out many obvious solutions, since it appeared to show that zero-mass particles would have to also exist that were simply not seen. According to Guralnick, physicists had no understanding how these problems could be overcome. Particle physicist and mathematician Peter Woit summarized the state of research at the time. Yang and Mills' work on non-abelian gauge theory had one huge problem. In perturbation theory, it has massless particles which don't correspond to anything we see. One way of getting rid of this problem is now fairly well understood: the phenomenon of confinement realized in QCD, where the strong interactions get rid of the massless gluon states at long distances. By the very early 60s, people had begun to understand another source of massless particles: spontaneous symmetry breaking of a continuous symmetry. What Philip Anderson realized and worked out in the summer of 1962 was that, when you have both gauge symmetry and spontaneous symmetry breaking, the Nambu-Goldstone massless mode can combine with the massless gauge field modes to produce a physical massive vector field. This is what happens in superconductivity, a subject about which Anderson was one of the leading experts. Text condensed. The Higgs mechanism is a process by which vector bosons can get rest mass without explicitly breaking gauge invariance, as a byproduct of spontaneous symmetry breaking. The mathematical theory behind spontaneous symmetry breaking was initially conceived and published within Particle Physics by Yoichiro Nambu in 1960. The concept that such a mechanism could offer a possible solution for the mass problem was originally suggested in 1962 by Philip Anderson, and Abraham Klein and Benjamin Lee showed in March 1964 that Goldstone's theorem could be avoided this way in at least some non-relativistic cases, and speculated it might be possible in truly relativistic cases. These approaches were quickly developed into a full relativistic model, independently and almost simultaneously, by three groups of physicists: by François Inglet and Robert Brout in August 1964, by Peter Higgs in October 1964, and by Gerald Guralnick, Carl Hagen, and Tom Kibble in November 1964. Higgs also wrote a short but important response published in September 1964 to an objection by Gilbert which showed that if calculating within the radiation gauge, Goldstone's theorem and Gilbert's objection would become inapplicable. Properties of the model were further considered by Guralnik in 1965, by Higgs in 1966, by Kibble in 1967, and further by GHK in 1967. The original three 1964 papers showed that when a gauge theory is combined with an additional field that spontaneously breaks the symmetry, the gauge bosons can consistently acquire a finite mass. In 1967, Stephen Weinberg and Abdus Salam independently showed how a Higgs mechanism could be used to break the electroweak symmetry of Sheldon-Glashow's unified model for the weak and electromagnetic interactions, forming what became the standard model of particle physics. Weinberg was the first to observe that this would also provide mass terms for the fermions. However, the seminal papers on spontaneous breaking of gauge symmetries were at first largely ignored, because it was widely believed that the theories in question were a dead end, and in particular that they could not be renormalized. In 1971–72, Martinus, Veltman and Gerard T. Hooft proved renormalization of Yang-Mills was possible in two papers covering massless, and then massive, fields. Their contribution, and others' work on the renormalization group, including substantial theoretical work by Russian physicists Ludwig Faddeev, Andrei Slavnov, Efim Fradkin and Igor Tyutin, was eventually enormously profound and influential. But even with all key elements of the eventual theory published, there was still almost no wider interest. For example, Coleman found in a study that, essentially no one paid any attention to Weinberg's paper prior to 1971 and discussed by David Politzer in his 2004 Nobel speech, now the most cited in particle physics, and even in 1970 according to Politzer. Glashow's teaching of the weak interaction contained no mention of Weinberg's, Salam's, or Glashow's own work. In practice, Politzer states, almost everyone learned of the theory due to physicist Benjamin Lee, who combined the work of Veltman and T. Hooft with insights by others, and popularized the completed theory. In this way, from 1971, interest in acceptance exploded, and the ideas were quickly absorbed in the mainstream. The resulting electroweak theory and standard model have accurately predicted weak neutral currents, three bosons, the top and charm quarks, and with great precision, the mass and other properties of some of these. Many of those involved eventually won Nobel Prizes or other renowned awards. A 1974 paper and comprehensive review in Reviews of Modern Physics commented that, while no one doubted the mathematical correctness of these arguments, no one quite believed that nature was diabolically clever enough to take advantage of them, adding that the theory had so far produced accurate answers that accorded with experiment, but it was unknown whether the theory was fundamentally correct. By 1986 and again in the 1990s it became possible to write that understanding and proving the Higgs sector of the Standard Model was the central problem today in particle physics. Summary and impact of the PRL papers. The three papers written in 1964 were each recognized as milestone papers during Physical Review Letters' 50th anniversary celebration. Their 6 authors were also awarded the 2010 J. Sakurai Prize for Theoretical Particle Physics for this work. 2 of the 3 PRL papers contained equations for the hypothetical field that eventually would become known as the Higgs field and its hypothetical quantum, the Higgs boson. Higgs' subsequent 1966 paper showed the decay mechanism of the boson. Only a massive boson can decay, and the decays can prove the mechanism. In the paper by Higgs, the boson is massive, and in a closing sentence Higgs writes that, an essential feature of the theory is the prediction of incomplete multiplets of scalar and vector bosons. In the paper by GHK, the boson is massless and decoupled from the massive states. In reviews dated 2009 and 2011, Guralnik states that in the GHK model the boson is massless only in a lowest-order approximation, but it is not subject to any constraint and acquires mass at higher orders, and adds that the GHK paper was the only one to show that there are no massless Goldstone bosons in the model and to give a complete analysis of the general Higgs mechanism. All three reach similar conclusions, despite their very different approaches. Higgs' paper essentially used classical techniques. Inglet and Brout's involved calculating vacuum polarization in perturbation theory around an assumed symmetry-breaking vacuum state, and GHK used operator formalism and conservation laws to explore in depth the ways in which Goldstone's theorem may be worked around.